A sequence for developing and communicating written reasoning for AP Physics 1 and 2. AP Physics 1 is sometimes the first course in which students are asked to use writing to communicate mathematically airtight deductive reasoning about physical quantities and relationships. You can use the mnemonics in this video to give students a scaffold for using multiple representations when solving physics problems, and to give students a scaffold for composing written arguments in English. Some of the material I will show you is based on an article that was published in the 2018 April issue of the Physics Teacher. Investigators familiar with science education research will recognize the mnemonics in this video as essentially a repackaging of existing scaffolds for solving physics problems and a repackaging of an existing scaffold for developing arguments. This is an example of a problem that asks for explained reasoning rather than for the numerical result of a direct computation. At the same time, Alice and Bob begin running from the start line of a straight racetrack toward the finish line at the racetrack's other end. Each runner almost immediately gets up to speed and then continues to run at constant velocity until Alice ends the race by crossing the finish line first. Let the direction pointing from the start line to the finish line be the positive x direction. Indicate whether Alice's average velocity v sub a, x, average during the race is greater than, less than, or the same as Bob's average velocity v sub b, x, average during the race. The symbol v sub x stands for the x component of a velocity. In this video, we use a common linguistic shortcut by referring to the symbol v sub x as simply velocity. Explain your reasoning. We can break up the problem-solving process into 5 steps. Neatly and graphically represent situations. We will make a drawing by carefully rereading the problem statement. At the same time, the problem statement has announced an instant of time that we label t sub I to indicate initial time. We have the freedom to choose to assign to this time the value 0. At the same time, Alice and Bob begin running from the start line of a straight racetrack toward the finish line at the racetrack's other end. We draw a racetrack, and we draw Alice and Bob both starting to run from the start line at the left, and both headed in the same direction toward the right, toward a checkered flag representing the racetrack's finish line. Each runner almost immediately gets up to speed and then continues to run at constant velocity. We draw a couple more representative copies of stick figures for Alice and Bob. Evenly spacing out each runner's figures is one way to show that constant velocity is almost immediately achieved and then sustained. Another way to depict practically constant velocity is to draw velocity vectors and motion diagrams using arrows having lengths that remain constant over time. Each runner almost immediately gets up to speed and then continues to run at constant velocity until Alice ends the race. We label the final time t sub f. Each runner almost immediately gets up to speed and then continues to run at constant velocity until Alice ends the race by crossing the finish line first. We draw additional copies of stick figures and corresponding velocity vectors for Alice and Bob to show that Alice and Bob individually sustain constant velocity motion until Alice reaches the finish line with Bob trailing behind her. Let the direction pointing from the start line to the finish line be the positive x direction. We decorate the racetrack with a labeled arrowhead to show that we are using the racetrack as a position axis. Drawing this position axis allows us to use tick marks to denote Alice and Bob's common initial position, which we have the freedom to call 0, Alice's final position, which is the finish line, and Bob's final position, which falls short of the finish line. indicate whether Alice's average velocity v sub a, x, average during the race is greater than, less than, or the same as Bob's average velocity v sub b, x, average during the race. We note this directive by writing a question mark to indicate that we are to compare Alice's average velocity and Bob's average velocity, or just as well, because Alice and Bob are performing constant velocity motion, Alice's velocity and Bob's velocity. Explain your reasoning. We write down a reminder in our sketch that we need to explain our reasoning. Graphically represent quantities and their relationships. We've actually already begun this step. We've graphically represented positions by using tick marks on a position axis and by using dots in motion diagrams, which also show velocity vectors. We can also draw displacement vectors delta x sub a and delta x sub b for Alice and Bob, respectively. In addition to labeling quantities on the sketch of the situations, we can graphically represent quantities on a diagram separate from the sketch of the situations. We set up an axis system displaying position x versus time t, showing that Alice and Bob both move from position 0 at t initial equals 0 to their respective final positions at time t final. On a graph of position versus time, the slope of the secant line from the origin to a second point is the average velocity belonging to a journey having the displacement and elapsed time represented by the origin and that second point. Identify relevant allowed starting point equations and inequalities. We drew both a sketch and a graph relating to average velocity, so it makes sense to write down an equation defining average velocity, which is the ratio of the displacement to the elapsed time. Analyze, which does not necessarily mean just algebra. Now that we've laid out features of the problem in the form of a sketch of the situations, a graphical representation of physical quantities, and an equation, we can analyze all three of these representations to solve the problem. The sketch of the situations illustrates that Alice and Bob begin and finish running at the same times. This means that Alice and Bob run for the same duration of time. We indicate this insight in three ways. In the sketch of the situations, we draw an arrow from t initial to t final and label this arrow delta t. This single copy of delta t describes both Alice's motion and Bob's motion. In the graph of position versus time, we also draw an arrow to highlight that there is a common single interval of time delta t. Near the equation defining average velocity, we draw a circled equal sign near the delta t in the denominator. In the sketch of the situations, the fact that the displacement vectors are drawn with different lengths helps us to see that Alice's displacement is greater than Bob's displacement. We also indicate this insight in three ways. In the sketch of the situations, we draw a vector showing the difference delta x sub a minus delta x sub b. In the graph of position versus time, we draw an up arrow pointing from Bob's final position marker to Alice's final position marker. Near the equation defining average velocity, we draw an up arrow near the delta x in the numerator. In the graph of position versus time, we can see that Alice's greater displacement implies that Alice's plot has a greater slope, and thus that Alice's plot represents an average velocity that is greater than the average velocity represented by Bob's plot. We use large letters to emphasize that the slope of Alice's plot is greater than the slope of Bob's plot. Using the equation for average velocity, we see that because compared to Bob, Alice has a greater delta x, which is in the numerator, while having the same delta t, which is in the denominator, Alice must have a greater average velocity, as indicated on the left-hand side of the equation using an up arrow. We document this finding in the sketch of the situations by ensuring that the illustration of Alice's velocity vector is longer than the illustration of Bob's velocity vector. We place a check mark in the option that indicates that Alice's average velocity is greater than Bob's average velocity. The problem statement requests that we explain our reasoning. Communicate. A tour guide plans the order in which to visit attractions before guiding tourists on a trip. In the same way, we will draw circled numbers to plan the order in which we will communicate key features of our reasoning before we write out our response in English. We will break up the planning of the English response using 5 prompts. 1. State and walk through a relevant relationship from allowed knowledge. Definitions, laws, and theorems are good examples of relationships belonging to allowed knowledge. On the graph of position versus time, we draw a circled 1 near one of the notes indicating that the slope of a secant line is an average velocity, and we draw a circled 1 near the equation that defines average velocity. 2. State what quantities, if any, are equal and why. In the sketch of the situations, we draw a circled 2 near the one single copy of delta t. On the graph of position versus time, we draw a circled 2 near the arrow on the time axis labeled by a single copy of the symbol delta t. And near the equation defining average velocity, we draw another circled 2 near the equal sign annotating the delta t in the denominator. Each of these 3 labeled symbols represents that Alice and Bob run for the same duration of time during the race. 3. State what quantities, if any, are altered or different and why. In the sketch of the situations, we draw a circled 3 near the arrow indicating that Alice's displacement is greater than Bob's displacement. On the graph of position versus time, we draw a circled 3 near the up arrow that also indicates that Alice's displacement is greater than Bob's displacement. And near the equation defining average velocity, we draw another circled 3 near the up arrow annotating the delta x in the numerator. Each of these 3 labeled features represents that Alice's displacement is greater than Bob's displacement. 4. So what? In the sketch of the situations, we draw a circled 4 near the question mark that reminds us to compare Alice's and Bob's velocities because, by following the dashed arrows representing this comparison, we are guided to look at representative velocity vectors showing that Alice's velocity is greater than Bob's velocity. On the graph of position versus time, we draw a circled 4 near the up arrow representing the conclusion that the steeper slope belonging to Alice's graph corresponds to her having a greater average velocity. And near the equation defining average velocity, we draw another circled 4 near the up arrow annotating the average velocity. Each of these 3 labeled features represents that Alice's average velocity is greater than Bob's average velocity. 5. Is there any quantity to analyze next? No, we've already obtained a conclusion that allowed us to check the appropriate option in the problem statement, so there's no need to feed what we've determined into any subsequent analysis of relationships and quantities. In this example, we drew multiple copies of circled numbers to show how specific features of each representation correspond to each other. When responding to a free response question under time pressure, it's perfectly fine to use circled numbers to label just those features of just those representations that most easily remind us of the points of the arguments that we want to compose. Now that we've numerically outlined key features of our reasoning, we can re-express our reasoning using English sentences. According to the definition of average velocity being the ratio of displacement to elapsed time, average velocity is proportional to displacement and inversely proportional to elapsed time. During the race, Alice and Bob travel for the same amount of time because A. They start running at the same time, and B. The race ends for both runners at the same time. Alice's displacement is greater than Bob's displacement because Alice crosses the finish line first. So Alice's average velocity during the race must be greater than Bob's average velocity during the race. We can remember key features of the argument developed in this example by seeing that selected letters from these prompts form the mnemonic reason. And we can remember steps for using multiple representations by seeing that selected letters from these prompts form the mnemonic sequence.